So several hundred years ago, there were many, many open questions in science, but two of them were why do things fall, and what causes orbital motion. So to make a long story short, Isaac Newton proposed a thought experiment. He said, "Okay, so let's say you're on a mountaintop, right? You're on a mountaintop and you have a cannon, and you fire that cannon, right? So we fire the cannon. What happens to the cannonball? Well, it falls, right? And we could describe that very well. In fact, his equations of motion helped us to describe that was a parabola, right? He said, okay, what if we fire it faster? Well, okay, it's going to go further. What if this is the tallest mountain on Earth? And we move the drawing. What if this is the tallest mountain on Earth and we fire it really fast? Right? No. There we go. We fire it really fast. Okay. Eventually, it's going to go further and further. It's kind of ugly. If you fire it fast enough, it'll come back around and hit the back of the cannon. At that point, you will have described orbital motion. So what Newton suggested is that whatever causes things to fall to the surface of the Earth is the same thing that's causing, say, the moon to go around the Earth. And the same thing, let's call it a force, that causes the Earth to go around the sun and every other planet to go around the sun. So he proposed a law. This is the Law of Universal Gravitation. The Law of Universal Gravitation. And the revolutionary thing about this is that he's suggesting that all matter attracts all other matter. All right. So the reason that the sun attracts the Earth is that they're both made of matter, and the reason that the Earth attracts a cannonball is because they're both made of matter. Right? They both have mass, and so they attract each other. So he wrote this law this way: I like to say F sub capital G equals G M1 M2 over R12 squared. All right, where M1 and M2 are the masses of these two different objects. So let's call them, M1 and M2. R12 is the distance that separates them. All right, so we could go center to center here. R12. And that force is on both of them. It's attractive always. And I've got Fg from 2 on 1 this way, and Fg from 1 on 2 this way. So they're an action-reaction pair. Okay, so the wild thing about this is that you can't... let me rephrase that. It's very difficult to measure the attractive force between Earth-scale masses. It turns out this capital G is a very small thing. Capital G is the gravitational constant. All right, and it is 6.67 times 10 to the minus 11. 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. All right, so you could ask, what is the attractive force between students sitting near each other in a classroom? Which just happens to be one of the example problems. So if we go here, this is in chapter 7. It is example number 10. All right, so what is the gravitational force between two students who are 65 kilograms separated by 0.6 of a meter? So simply just calculating the force. F sub g, again, is g m1 m2 over r12 squared. Plugging in, it's 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times 65 kilograms twice divided by 0.6 meters squared. That makes the units work out to newtons, which is fabulous. This turns out to be 7.8 times 10 to the minus 7 newtons, which is about the weight of a hair. So this, compared to, say, the gravitational pull of the Earth, is minuscule, right? Tiny, tiny thing. So you don't notice it because there's another force on you that's much, much bigger, right? Plus, sure, you're gravitationally attracted to the student on your right, but you're also gravitationally attracted to the student on the left. So there are lots of other forces that that would act to cancel these out. Okay, so this suggests actually a new definition for weight, right? Because we already have talked about gravity. We have defined something for gravity already. We've said, well, don't we know that weight is m little g? Haven't we defined that already? And I would say, yes, we have. And this is where our new definition does not contradict this, it complements it. All right, let me explain. So weight is the gravitational attraction between the object that has weight and the Earth, right? So mass 1 is maybe this guy, and mass 2 is the Earth. And this is why the weight of something is a force that you notice versus the gravitational attraction between two objects just in a room. Because the mass of the Earth is very, very big. Right? How big? I'm glad you asked. I think I have that in the... No, I think it's 5.98 times 10 to the 24 kilograms. So let's write that down. Mass of the Earth is 5. I'll double check that. That's what Google's for. It's 5.97 times 10 to the 24. Sure. 5.97 times 10 to the 24 kilograms. Which is, much bigger than the mass of a student. Okay, so if we were going to write the gravitational attraction between this student and the Earth, you could say G m1 times the mass of the Earth divided by, that mass 1, whatever it is not a fixed distance from any point on Earth, right? Or from the Earth. It's really close to this part, but really far away from this part. Right? So how would you figure this out? Well, you could actually integrate. If you assume that the Earth is a uniform solid, like a uniform sphere, you can integrate over the entire Earth to figure out what this gravitational force is. Basically, you're integrating G m1 dm over r squared. You're integrating this thing over mass. All right. How do we know how to do that? Isaac Newton invented calculus to prove this. All right. This is why it took him some years to actually publish his work, because he had to invent calculus to be able to prove that you can treat a spherical solid like a point mass at its center. So the r that we use is the distance to the center of this. In fact, we could say capital RE, which is the radius of the Earth. And the radius of the Earth is 6,357 kilometers. So let's write that down. Radius of the Earth is 6,357 kilometers, or like 6 times 10 to the 6 meters. So 6 million meters is the radius of the Earth. Okay, so we really can say R, in fact, RE squared. Okay, great. Except, again, we want to know that this does not contradict what we already knew. So, so if these are both true, so I'll underline them both. If this is true and this is also true, they need to be equal. These are both expressions for the force that the Earth applies to that mass. Right? So let's set them equal and see what we get. Okay, so weight equals force sub g. Weight is m times little g. And force sub g is capital G, mass of the Earth, mass of the object divided by radius of the Earth squared. So it looks like mass of the Earth goes away, and I get this expression that the acceleration due to gravity is the gravitational constant times the mass of the planet divided by the radius of the planet squared. Let's see if that pans out. All right, in fact, let's just erase u and just solve it, right? So what is that? 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 6.357 times 10 to the 6 squared. All right, so let's plug all those in. 6.67 plug it in too if you want. Here's what I get. 9.85 and the digits go on. Let's round that to 9.8. And what are the units? Well, I guarantee you they turn out to meters per second squared. So look at that. Okay. So we now have an expression for the acceleration due to gravity on another on another planet, right? So this was true for Earth, me over re squared. And again, we got 9.8. Maybe it would round to 9.9. But again, the Earth isn't a perfect sphere. So the radius there has got to be some kind of average, right? In fact, I think what I gave you is the polar radius, but the equatorial radius would be a little bigger. Here, the equatorial radius is 6.378, and the polar radius is 6.357. So somewhere in between there would actually be accurate. But this also lets us calculate the acceleration due to gravity on, say, the Moon or Mars, or if we could measure the acceleration due to gravity on one of those places, we could use that to find some other bit of information. So that's kind of interesting. Let's look at another example. I would like to look at example 14. Example 14 says the free fall acceleration on the surface of a planet is 20 meters per second squared. The radius and mass of planet 2 are twice that of planet 1. What's the free fall acceleration on planet 2? Okay. So G1 is 20 meters per second squared. I do not know the planet's mass or the planet's radius. Right? But I do know that on planet 2, it has twice the radius, so I can say R2 is twice R1, and mass 2 is twice mass 1. The question is, what is G2? Okay, so this is an interesting question, again, because we're not actually plugging numbers in, right? This is a proportionality equation. So G in general, again, is G m planet over r planet squared. Just a bit of notation here. When I use a capital R, generally I mean the radius of a planet. When I use a lowercase r, generally I mean the radius of an orbit, and we'll see that in future problems. Okay, so what do I know? Well, G1 equals G m1 over r1 squared equals 20 meters per second squared. Right? And G2 is going to be G m2 over r2 squared. And I don't know what that equals, but I do know that m2 is twice m1. So look, I'm going to take this and plug it in here. And I'm going to take this and plug it in here. So capital G m2 is 2m1 and r2 is 2r1 squared. So what do I see? I see that one of the 2's goes away, right? The 2 upstairs is just a 2. The 2 downstairs is squared, so that's actually 4. So that's 2 over 4, which is 1 over 2. So this whole thing works out to 1/2 G m1 over r1 squared. But look, G m1 over r1 squared, that's 20. Right? So what works out here is that G2 is half of G1. G2 is half of G1. So it must be 10 meters per second squared. So what's really interesting here is that I didn't have to use capital G at all. Right? I didn't have to know the mass or radius of planet 1. All I needed was the ratios to figure this out. Okay, that's kind of cool. So let me answer one more question, or really ask and then answer one more question, and that is, okay, so we're on the Earth, and we are held on the Earth by the gravitational force between us and the Earth. And the question is, aren't we also pulled by the sun? And the answer is, well, yeah, we are pulled by the sun. How massive is the sun? Well, the sun is 2 times 10 to the 30 kilograms, so that's 1,000,000 times more massive than the Earth. A little less than 1,000,000 times more massive than the Earth. It's like, okay, that feels like it should have a much, much bigger force. But it's also further away, right? The distance from the Earth to the sun is 1.5 times 10 to the 11 meters versus 6 times 10 to the 6 meters. So I guess the question is, what is the, so let's go to the example. The example is, not this one, is example number 11. Oops. So let's say we're on the Earth's surface. What is the ratio of the sun's force on us from the Earth's force? And I have a sense like the sun should have a smaller force because we're not being pulled through the sun. We're staying on the Earth, right? So where's the sun? Here's the sun. And here's the Earth, and here's us on the Earth. And the question is, what is the ratio F sun to F Earth on us at the surface of the Earth? Okay. So we can do this. Basically, I need to know a couple numbers, right? Again, the mass of the sun is pretty close to 2 times 10 to the 30 kilograms. And the mass of the Earth is pretty close to 6. It's 5.97 times 10 to the 24 kilograms. Our distance to the center of the Earth is about 6 times 10 to the 6 meters, and our distance to the sun, the sun-Earth distance, is Ooh, that's tricky. Not the number, but the notation. So I did a capital R here, but when I use a capital R, generally I mean the radius of the planet, but really what I need is the distance to the sun. So we'll say distance to the sun, it's 1.5 times 10 to the 11 meters. These are all things you can Google, right? Or they're in a table in the textbook. Okay, so now we're ready to do this. So it's just a force divided by a force, so we can fill out the equation twice. We've got G, mass of the sun, times mass of the person, right? Divided by the distance to the sun squared. And that whole thing divided by, nuts. The whole thing divided by the force, come on man, between the Earth and the person at the surface of the Earth. So that's radius of the Earth here, squared. Okay, so what cancels? Well, the mass of the person in capital G. And what's left here is the mass of the sun divided by the distance of the sun squared times the radius of the Earth squared divided by mass of the Earth. If you're uncomfortable with dividing by the fraction, you can just leave it. You can solve the top fraction and the bottom fraction and then plug it and then just take the ratio. At this point, though, it's just numbers, right? We just plug these in. So we will. 2 times 10 to the 30th divided by 1.5 times 10 to the 11 times squared 6 times 10 to the 6 squared divided by the mass of the Earth, which is pretty close to 6 times 10 to the 24. That's it. Okay, so if you do that math, what you get is 0.006. 0.006. That's rounding a little bit. Okay, does that track? Does that make sense? Well, that means that the force of the sun on us is 0.6% the force of the Earth on us. So we don't really notice it. Plus, I drew it as the opposite direction, but if it were nighttime, right, you would be standing on the opposite side of the Earth. Or, maybe sleeping, I don't know. But then the force would actually be additive, right? You would feel a little heavier at night and a little lighter at noon. But again, it's 0.6%. There are other effects that are actually bigger than that. Things like the fact that the Earth is rotating, and whether you're standing on the equator or the pole or somewhere in between. Okay, so next up will be orbits. We'll talk about that pretty soon.